look at some examples from Chapter 8 calculations. So in Chapter 8, it's all about circuits, energy, power, current, resistance, all that good stuff. So looking at the first problem, we have a sound machine using a 3-volt battery with 0.5 A, so A is amps, of current running through. And it's asking us to calculate the resistance. So this is a classic physics problem, so we're going to approach it the same way we have been, by writing down our knowns and our unknown, and then matching it with the appropriate equation. So what we have here is 3.0 V. So that is a voltage. Volt is just V. That's the variable for voltage. Our next piece of information is 0.50 A. So A is amps, and that is current, and it even says 0.5 amps of current. So it tells you what variable you're looking at with that 0.5 A. Now current is represented by the letter I. And all of this is indicated on your Chapter 8 equation sheet. It says I is equal to current in amps. So all of that information should be available to you to help you get through these problems a little easier. So my I value is my current, is 0.50 amps. And the last piece of information is saying calculate the resistance. So resistance is R. So the 3 variables I have are V, I, R. So Ohm's law is going to help us here, which is V is equal to IR. And in this case, we're going to need to rearrange that equation to solve for R, because resistance is what they're asking us to solve for. So I want resistance by itself, so I need to get rid of that I. I need that I, the current, to go on the other side of the equal sign. So to get rid of it, I'm going to divide by I, because then it cancels out on this side of the equation. Whatever I do to this side of the equation, I need to do to the other. So I'm going to get R now by itself, because the I is canceled, is equal to V over I. So now I can plug in my voltage and my current into this equation, divide them to solve. So my voltage was 3 volts, my current was 0.5. 3 divided by 0.5 is 6. And since I've made so many mistakes here and there on these videos, I'm going to double check that. So it is 6. And then for units on resistance, it's ohms. So you can either write this funky symbol that means ohms, or you can just write OHMS, either one. All right. Let's look at the next problem. So this first one, before we move on, there is just one resistor in the entire circuit. So remember, to have a circuit, we need a voltage or a battery source, or plug in some sort of voltage coming from some sort of source. We need a current, and then there's also a resistor, which is being powered by that current and that voltage. So there's just one resistor in this first problem. The second problem now, we're looking at 4. So 4 light bulbs. So each of those light bulbs is called a resistor. And this specific problem is telling us that they're in a series. Okay? And it's important to know whether they're in series or parallel, because there's different ways to calculate based off of the arrangement of the resistors. Okay, so when we look at series, these 4 light bulbs, how we represent it, so here's our voltage. We have an R1, we have an R2, we have an R3, and then an R4. So those squiggly lines, this is how you're going to see them on the exam. The series circuits will be represented like this. So these squiggly lines here, these are our resistors, our 4 light bulbs. So R1, R2, R3, and R4. Okay, so 25 ohms, 50, 100, last but not least, oh, he was 75, sorry about that, 75, and then 100. So one of the characteristics of series, notice, is that all of these light bulbs are connected along one line. So when the current runs through, it's going to be the same current running through each light bulb. Okay, so the current's going to be the same for every light bulb. That's different than parallel. The current's not the same for each resistor. So series, it is the same because there's just one line. So what happens if one of these light bulbs goes out, I've now disrupted the current, and the rest of the light bulbs are also going to go out. I mean, if you watch the PowerPoints on this, this probably all sounds familiar. All right, so I have 4 light bulbs in a series, one right after another, with 25, 50, 75, and 100. Okay, it wants us to calculate 2 things. The first part is saying calculate the total resistance, and then the second part is saying then calculate the current. And since it's a series circuit, it's the same current for each resistor. All right, let's approach the first question, calculating the total resistance. So for this one, there's 2 possible choices when you're looking for total resistance, and that's R total. You have an R total for a series circuit and an R total for parallel. So you need to know which one you're looking at so you're using the appropriate equation. The nice thing about the series circuit is they're simply additive. You can just add those resistances together. So in this case, the R total for the series is going to be R1 plus R2 plus R3 plus R4 because we have 4 total resistors, 4 light bulbs. So I'm just going to take these numbers and just add them together. 25 plus 50 plus 75 plus 100. Should get 250. And it's resistance, so it's that little ohm symbol. Okay, so here is my total resistance for that series circuit. So now approaching the next question, it's asking us to solve or to calculate for the current given the light is plugged into a 110 volt outlet. So it's giving us another piece of information. So we have our R total. We just solved for that. Then we have a voltage. So we also have a V value. And it's asking us to solve for a current, I. So if you'll notice, this is the same as the question up here, same equation, okay? Because we have VIR. Down here, we also have VIR. The only difference is that instead of one resistor, we had multiple. So we had to calculate the R total before we could move on to the next steps, okay? So let's write down the Ohm's law equation again. And this time we're going to rearrange to solve for our unknown, which is I. So V is equal to IR. That's the equation we want to use because we have voltage, we have total resistance, and we're looking for I. So this time we want I by itself. To get I, or the current by itself, we need to get rid of that R value. So to get rid of it, I'm going to divide by R total. Whatever I do to one side of the equation, I'm going to do to the other. So R total is going to cancel on the right-hand side of the equation, making I by itself. To solve for current, I'm going to take the voltage divided by that total resistance. Plugging in, I get 110 on top for the voltage, 250 for my R total. And that gives me 0.44. So 0.44 amps of current is running through that series circuit. So the last 2 problems we're going to look at in the chapter. The first one, we have an iron, I'm talking about it like iron that you iron clothes with, being plugged in to a 110 volt outlet. We're going to calculate the current if the iron uses 250 watts of power. Right, so let's start by making our list of knowns and unknowns, just so we're making sure that we're using the correct equation. So we have 110 volts, and that is a voltage, it's variable. Then we have a current drawn, that's the question mark. Okay, so what is current? What letter does current belong to? What variable? I. And it says the iron is using 250 watts of power. So it's telling us that that watts is a power, but if it didn't say the word power, we could figure that out based off of the units. So the 250 W is the power. So it's not Ohm's law because we don't have a resistor. So we're looking at a different equation. So we need to find one that has power, current, and voltage. And the equation on the chapter 8 equation sheet that I see with that is P is equal to VI. We are solving for I, the current, so we're going to need to rearrange this equation. To rearrange it, we need to get rid of the V, get that on the other side. So we're going to divide by V on both sides, cancels out on the right side. We now have the I alone. Power divided by the voltage will give us our current. So power is 250 watts. The voltage is 110. So 250 divided by 110 gives me, how many sig figs? 2? So 2.3. So my current of 2.3, and then what are the units on current? Amps. Very good. Okay, so let's look at this last problem now. Very similar. We have a small air conditioner unit using 3.6 kilowatts. Calculate the current drawn at 110 volts. So you're probably wondering why all of these have a voltage of 110. That's standard voltage for most plugins. So that's why it's so consistent in all of the problems we're doing. So we have the voltage. Let's just write that one down right away. This 3.6 kilowatts. So kilowatts or watts belongs to what variable? That would be a power. But notice this time it's in kilowatts. In order to use this equation, we need it in watts. So we are going to have to convert that. Okay, so let's just write that over here so that we remember to do that. So convert 3.6 kilowatts to watts. And then current is what we're looking for once again, right? The current drawn. So that's our I value. So before we do the equation portion, we need the correct units on the power. So to go from kilowatts to watts, it is metric to metric, because remember we said to remember metric to metric, you're looking at just that last letter, and it's watts, watts. So metric to metric, we can use that King Henry died drinking chocolate milk. And in this case, what's going to go in our empty space is a W for watts. So we're at the kilo over here by the K. We want to get to the W, the watts. So we have to move that decimal point 1, 2, 3 times to the right to get it there. Okay, so let me write my number down here so we can see this a little bit better. You always start at the decimal, and we just moved it 3 times to the right. So 1, 2, 3. My new decimal point is going to be here. So what's going to go in those empty spaces? Zeros. So 3.6 kilowatts is equal to 3,600 watts. So that's the value that I'm going to use when I insert these numbers into my equation. Now, it's the same as the equation above. Power is equal to voltage times current. We're rearranging it once again to solve for I, so it's the same steps as before. Divide both sides by V. So now we can plug in power on top, voltage in the bottom. So 3,600 is going to go on top. My 110 voltage is going to go on the bottom. And this time we get, rounding up to 2 sig figs, 33. And current is measured in what units? Amps. So we have 33 amps of current. So more current is needed for a stronger resistor, which makes sense. All right, that takes care of chapter 8. All right, now let's look at those same 4 light bulbs that we saw in the series circuit, but now placed in parallel. So notice we are solving for the total resistance, but not the current in this one. Okay, and the reason we're not calculating the current is because the current is different for each of the resistors when it's a parallel circuit. So let's draw a picture so we can kind of understand this a little bit better. So let's do a parallel circuit this time. So I have my voltage source here, and I would have one light bulb, two light bulbs, three light bulbs, and four light bulbs. Okay, so these would be my R1, my R2, my R3, and my R4. Now this time, so imagine the current going around this guy. So the current leaves the voltage source, and when it gets here, that current is going to split. Part of it's going to go towards R1, light bulb 1, to light that light bulb up. The rest of the current is going to continue on down, and when it gets to this junction, it's going to split again. Part of it going to light up that light bulb number 2. The rest of the current continues on down, splits again, and then finally goes around. So since the current is splitting several different occasions, it's not the same current going through each resistor. The current's actually additive. So that's why we're only calculating the total resistance and not the total current, because we would have to calculate the current for each resistor in a parallel. So we would have 4 different current calculations to do that one, and we're not going to go that in depth. So let's just look at how to calculate the total resistance when they're in parallel. So for this equation, you're going to those total, you have 2 total resistance equations on your equation sheet, and the one for parallel is 1 over R total is equal to, in this case, since we have 4, I'm going to have 1 over R1 all the way up to 1 over R4. So I'm going to plug in these values, just the 25, the 50, the 75, and the 100. So I have 1 over 25 plus 1 over 50, not 15, excuse me, 50, plus 1 over 75, and then plus 1 over 100. Okay, so there's a trick to this one, because whatever you get once you do that is not your final answer. So let's calculate this first. 1 divided by 50 plus 1 divided by 75 plus 1 divided by 100. Okay, so I get 0.08333 repeating. Okay, this is not your R total. Look, this is 1 over R total. So what that means is I need to flip that. So how do I flip that? On your calculator, you should have a button that looks like X minus 1. And what this is, it's called the inverse button. So you're going to take whatever answer shows up on your calculator when you calculate for total resistance in a parallel circuit, and you're simply going to go and you're just going to press that button and the equal sign. Because what that button does is it takes your answer and flips it so that the answer becomes R total instead of 1 over R total. Okay, so my answer that I get then is 12. 12 what? Ohms. All right. Now let's look at another problem. So let me move this up a little bit. The next problem, we are going away from Ohm's law. So we've seen all the examples that you'll need to know how to do requiring Ohm's law, voltage, current, and resistance. Now we're going to look at energy and power. Okay, so in number 4, a lamp with 60 watts light bulb, with a 60 watt light bulb is left on overnight for 12 hours. How much energy does it consume? Okay, well, let's figure out what we got going here. We have a 60 watt light bulb. Looking at the units, what does watts mean? What does watts stand for? Watts stands for a power, so that's going to be my P. The light bulb is left overnight for 12 hours. So 12 hours, that is a time. Okay, and I just noticed something here. Do we ever want time in hours? We do not. So we're going to have to convert that to seconds. And then last but not least, how much energy? Okay, so here's our variables. We have a P, a T, and an E. So when we go to find the equation, we're going to look for an equation that has those variables in it. Before I do that, let me do this conversion here. Okay, and I'm going to do that off to the side. So convert 12 hours to seconds. Okay, so I'm going to need some conversion factors. All right, well, how many minutes are in 1 hour? 60. But I'm still not at seconds. So how about how many seconds are in a minute? 60. Okay, so those are our conversion factors. We start our railroad tracks. We always start with what's given, the 12 hours. I'm going to use this first conversion factor, the top one here. Do I want my hours on top or bottom? I want it on the bottom so it cancels. That's going to put my 60 minutes at the top. So if I were to stop here, just multiplying 12 times 60, that would tell me how many minutes are in 12 hours. But I'm going to keep going and use this second conversion factor to get to seconds. So to do that, I want the minutes now on the bottom so they cancel. That's going to put my 60 seconds on the top. So to get the total seconds, I'm going to take 12 times 60 times 60. 43,200. Okay, so now let's find the equation we need. So looking up the equations with energy, power, and time, we have E is equal to P times T. So this one we do not have to rearrange, we can just plug in. Our power is 60. Our time is 43,200. So huge number. And remember, when we're measuring energy, it's always measured in joules. The one time we had an exception to that rule was when we measured heat energy in the last chapter. That was in calories for the heat energy. So I want to 2 sig figs to 1, 2, 3, 4, 5. So you could write this in scientific notation as well. 2,600,000 joules of energy to keep that lamp on for 12 hours.